Okay, so we'll go back to another video. So here we have a definite integral of a trigonometric integrand. So we have from 0 to pi over 2 of x times the absolute value of sine square of x minus 1/2 dx. So with a combination of this, and especially with the absolute value function added into our integrand, we have to be a little bit careful on how we're actually taking things into this sort of approach. So of course we have a sine square x, so you probably might expect to use some sort of trigonometric identity to help simplify some things out, which we will be using, of course. And mainly, as mentioned, the absolute value, that's actually the biggest challenge on how we're going to tackle such integral, because when it comes to absolute values, yes, those are positive functions, so we have to think of this in terms of a case-by-case situation. As you know, with absolute functions inside of as an integrand of what we're taking the definite integral over, we have to use this sort of trick that, as you notice, that we actually have to split this up as a sort of sum of difference, or sum/difference of integrals, such that it actually depends on our bounds of integration we're actually utilizing around/working with. So with that out of the way, that's pretty much just that. So why don't we actually just jump right in? Okay, so to make things a little simpler, so capital I is going to be our given integrand. Why don't I actually multiply and divide a 2? So of course, with that being a constant moving inside of our absolute value, so that means we can actually simplify this out just to get rid of the fraction, and of course divide a 2 so it's still constant, so that means I have a 1/2 outside of our integral. So 1/2 multiplied the integral from 0 to pi over 2 of x, and then multiply by the absolute value, so that means I have 2 times sine square of x, and then subtract 1, close off that absolute value, and then dx. Alright, so let's actually use a trigonometric identity that says that 2 sine square of x, and then subtract 1, that's actually simply just going to equal negative cosine of 2x. Okay, so of course without that negative, you just multiply negative both sides, and that's the well-known trigonometric identity for the double angle formula. So why don't we actually take the absolute value of both sides? So I have 2, then sine square of x, then subtract 1. So that means I'm taking the absolute value of negative cosine of 2x over here. So with properties of absolute values, that means I'm basically taking the absolute value of -1 multiplying by the absolute value of cosine of 2x. So of course, the absolute value -1 is simply just equal to 1. So that means that just leaves us with the absolute value of cosine of 2x. So with that in mind, now we can actually just do a bit of substituting over here. So now that will yield us with 1/2, then the integral from 0 to pi divided by 2 of now just x multiplied by the absolute value of cosine of 2x, and then close it off with dx. So with this in mind, now we can actually do a little bit of a u-sub over here. So that's, some elementary techniques we'll be using. So why don't we actually let u equals 2x. And since we have an x over here, let's actually solve that by itself. So why don't I actually change this to say, so we have that x is simply just equal to u divided by 2. Okay, and that's great since we have to differentiate both sides. So we have a dx differential standalone on its own that we can actually substitute afterwards. So I have that dx is then just simply going to equal to just 1/2, and then multiply with du. So now we just put in that substitution over in. Then now what we have now is actually just plugging everything back into here. So I have 1/2, then times the integral. So don't forget to change your bounds. So I have 0 over here, that means that's just going to be 0. And if I have pi over 2 back to over here, so that means that's just going to be pi. And now just simplify, or rather substitute some stuff back in for x, the new x in terms of u. So what we have is u divided by 2, and then multiplied by cosine of, so the 2x, so that means that's just going to be cosine of u, then close up that absolute value, and then simply just multiply the differential over here. So we have 1/2 du. And then if we can simplify things even further, what we have now is that I can actually factor out the 1/2 over here. And so also factoring out another 1/2 from over here. So now that'll just lead us to have 1/8 of our integral from 0 to pi of just u multiplied by cosine of u, and then du. Okay, great. So what can we do here? So let's actually now perform yet another u-substitution. We'll actually call this variable t. So let's actually go into a different marker for this and continue forward with the substitution. Okay, so now for our new substitution, we're gonna let be u. We'll let this be equal to pi, then subtract t. Okay, so now to differentiate both sides, so that means I have that dt is simply just going to equal to negative, or I'm sorry, du is going to equal to negative dt, Okay, and so with this, now we can actually just now perform our little substitution. So what we have now is, so far I is actually just going to be, so we have 1/8 and then multiply with our integral, so change the bounds. So if I have pi for u, so that means t is just going to be 0, and if I have 0, then that means on the bottom that's just going to be pi. And so now we just put in the substitution for u, so that means I have pi, then subtract t, and then now multiply by cosine of, now we have just pi subtract t, and then close that off. Well, not yet. Let me actually now multiply the new differential. So multiply with negative dt. And what's great is that I have to switch the bounds anyway, and that cancels out the negative. So that means now we're just left with 1 divided by 8. Then multiply from 0 to pi of pi subtract t, and then multiply by the cosine of pi, then subtract t, and then dt. Okay, and so what's next is, now notice that inside of our absolute value function over here, cosine of pi minus t, well, that's actually follows a nice symmetric identity to, the trigonometric functions. So what that says is that if we have cosine of pi minus t, absolute value of that, so simply that's just the same thing as saying the absolute value of negative cosine of t, just like from earlier before, and we can actually deduce that this is actually just simply just the absolute value of cosine of t. So we can actually now just do a little bit of the substitution we just replaced. And so now we have that. And also notice that this is still the same thing as capital I, because what the next step is going to do is it's going to be a game changer. So what we have that so far is I is simply just 1 divided by 8 multiplied by the integral from 0 to pi of, pi subtract t, and then multiplied by cosine of t, and then simply put that off with dt. And so now what we're going to do is we're actually going to take this equation over here. So let me actually box our equations first before we do anything. So we're actually going to box, this is the equation that's being boxed. And then another one we're actually going to box is this one over here. It's a different color, but don't worry about that. So the two boxes over here, they're the same thing, equal to each other to I. So what we're going to do is that we're actually going to take these two integrals and add them together. And so that gives us 2 times I, so double the quantity. So what we have now is 2I is going to be just equal to, and then this is the sum of integrals over here. So I have 1/8 multiplied by the integral from 0 to pi. And this is also great since they're also in the same bounds as well, our integration bounds. So what we have is, so this is actually t, and of course this is just a dummy variable, so I'll just replace this back with t instead. So it's still the same thing, we're integrating in the same variable, it's still the same thing either way. So t times cosine of t, and then dt, then now we can now add this with, so 1/8, and then multiply by the integral from 0 to pi of pi subtract t, and then multiply by the absolute value of cosine of t, and then dt. And then you can actually just combine the sums together. So that means this is actually just going to cancel out the t. And not only that, we're just going to be left with just pi, and pi is a constant yet again. So of course we can actually just factor that out. And so that'll yield us with pi divided by 8, and then multiplied by the integral from 0 to pi of just the absolute value of cosine of t, and then dt. All right, so now this is where the biggest challenge goes from here. The absolute value of cosine of t, how do we evaluate such function as that? Well, as I mentioned, absolute values, of course, you have to look at this at a case by case, and because it's a positive function, that we have to look at it and split this up into different domains, such that afterwards we can now just take the sum or slash difference, because notice that we're actually going to have some kind of negative function involved in this. So what we have is that specifically that the absolute value of cosine of t, so we actually have 2 different functions we're looking at. We have the positive, so cosine of t, and that's actually just from, of course, that t is in the interval from 0 to pi divided by 2. And then afterwards, it becomes negative cosine of t, such that t is in the interval from pi divided by 2 all the way up to just pi. So that means we're actually taking two different functions, and we're actually gonna now, since add them, or in this case subtract, since we have a negative, and then that actually yields us with a case-by-case solve, such that now we're just dealing with pi divided by 8 multiplied by the integral from 0 to pi over 2 first of just positive cosine of t, then dt, and then subtract pi divided by 8 multiplied by our interval from pi divided by 2 to just pi of cosine of t, and then dt. And we know cosine of t, we know the basic antiderivative of that is simply just going to be sine of t. And so what we have is pi divided by 8, so sine of t and evaluate from 0 to pi divided by 2, then subtract pi divided by 8 multiplied by, so antiderivative sine of t, and then we have just from pi divided by 2 to pi. And of course, we have that pi and 0. If we plug in for sine of t, those are just simply going to be 0. And then if I just plug in pi over 2, that's actually simply just going to be 1. And so over here, that's actually going to be 1 as well. But since it's subtraction, that becomes a negative. And so what we have is that it's pi over 8 times 1 minus pi over 8 times negative 1, which yields us just 2 pi divided by 8, or in other words, just pi divided by 4. We're not done yet, since that's just 2 times I is equal to pi over 4. All we have to do now is just divide by 2, and so therefore capital I, our integral that we need to solve for, is simply just going to equal to just pi divided by 8. And so that closes it off. It comes down to a nice and simple answer just like that. Usually just breaking it down case by case, well, for specifically our absolute value of the trigonometric functions, and it just leads to a nice result just like that. So there you have it. So yeah, that's pretty cool if you ask me.